Here we discuss how we can describe the state of stress inside of a fluid and how that translates into an expression for our stress tensor. And we start by discussing how stress looks like in a fluid which is entirely at rest. So in a fluid at rest, that means that it is in static equilibrium, for which the velocity field, we assume the velocity field here is equal to 0. So there is no motion. Okay, so now if I'm representing flow, of course there is no flow because we're assuming u is equal to 0. But let's think we are interested in this particular point, and let's assume in particular that we can, because there is no preferential direction at this point, let's say that we are in the coordinate system where our stress tensor is diagonal. So that means that we have two principal stresses, one in the y direction and one in the x direction. So that would be, let's think about here, this being the stress exerted onto in the y direction. That would be our principal stress in the y direction. And let's say here that would be our principal stress, sorry, in the x direction I meant, and here that would be our principal stress in the y direction. Right? And the question is the following: if we are in a fluid in a static equilibrium, can Txx and Tyy be different? Now if you think about this, if you had Tyy which was larger than Txx, then the fluid would start to move in this direction, right? Because it starts to flow. And so what you see from this simple thought experiment on how a fluid behaves, well, if the fluid is at rest, then the stresses, the principal stresses, have to be equal. So Txx here has to be equal to Tyy. So for a fluid at rest, the principal stresses are equal. So that means that not only is our matrix diagonal, but our matrix really is just the identity matrix. So it's a diagonal matrix with all of the diagonal term equal to the same value. And now what is this value? This is precisely what we call the pressure, or in that case the static pressure. Right? So our stress tensor will be equal to this matrix here, which we can also write minus P times the identity, P here being the pressure. And the identity matrix here, again, remember, is the matrix which has only ones on the diagonal and which has 0 elsewhere. All right, so we have our first expression for the stress tensor in a fluid at rest. The stress tensor is equal to, so the stress tensor T at every single location and time is equal to minus the pressure. This is a field, so in general P might be a function of position and time times the identity matrix. So from this stress tensor, we can start to deduce what forces are exerted by fluids at rest. Okay, so if we consider the Cauchy momentum equation, we can see how the Cauchy momentum equation simplifies for a fluid in static equilibrium. So what is our momentum equation for a fluid in hydrostatic equilibrium? Now momentum equation, remember we derive, it's the Cauchy momentum equation. So we have that rho times the material derivative of u is equal to the divergence of our stress tensor plus our body forces. And here we assume that u is equal to 0 because we are in static equilibrium. Therefore, the left-hand side is equal to 0. And we have the divergence of our stress tensor, which is minus p times the identity. And that is equal to our body forces. But the divergence of minus p times y times I is equal to the minus the gradient of p. And therefore we are left with the following equation. Our momentum equation reduces to an equation for the gradient of p, and that is the gradient of your pressure field, of your static pressure field, is equal to the external forces. I should say the external body forces. And now if assuming the only body forces that apply are gravity forces, then we can reduce our momentum equation to the gradient of the pressure field is equal to rho times the acceleration of gravity. And if you write this in Cartesian coordinate, you essentially have that partial p partial x is equal to 0, partial p partial y is equal to 0, and partial p partial z is equal to minus rho g. Note here that partial p partial x implies that p is independent on x, and partial p partial y implies that p is independent on y, and therefore p is only a function of z. So in that case you can also write a straight p dp dz is equal to minus rho g. This is the equation for the hydrostatic pressure.